When we did linear dynamics, one of the important physics diagrams that we did was called a free body diagram. This particular diagram drew all the forces acting on one object from the center of mass of the object. When we do rotational dynamics, however, it is sometimes more useful to draw forces at the point of application instead of a free body diagram. Why do we want to do this? Because where forces are applied is very important when discussing torque and rotation. Here's a good example of what we're talking about. In this particular picture, a painter is standing on a ladder. The ladder is held steady in place as it leans against the wall and is propped up on the driveway. If we were to look at the forces acting specifically on the ladder and only the ladder, we would come up with the following 6 forces. The first force is going to be the weight of the ladder itself. Force of gravity is going to be equal to the mass of the ladder times g, which I am representing by m sub l multiplied by g. That vector is pointed downward, as shown to the left. Next, we look at normal forces. There are going to be 2 normal forces acting on the ladder in this case. The first one is going to be the normal force that is pushing the ladder up that is done by the driveway. I have designated this normal force as F subscript n comma d for driveway. That force is pointed straight up as shown to the left. The third force and the second normal force is going to be from the wall that the ladder is leaning against. The wall is going to push outward on the ladder to the left, and I'm designating that force as F sub n comma w, with w standing for wall. Next, we look at friction forces. There are 2 static friction forces that are acting on the ladder, since we are assuming that this ladder is not sliding. First, there is the static friction force between the driveway and the ladder. Since the ladder would naturally want to slide to the left if there was no friction, we can assume that the static friction force is going to be pointed to the right. I have called this static friction force, comma, D for driveway. There is another static friction force because if there was no friction, then the ladder would also begin to slide down the wall. This means that the static friction force is pointed up. I've designated this as static friction force, comma, L, which I should not have done. I wanted to do that as a W, sorry. For wall. There, that makes a little more sense. The final force is going to be another force of gravity, but it takes a little thinking to get there. Technically, what we have is the painter standing on the ladder, and because the ladder pushes the painter up, that means the painter pushes back on the ladder by Newton's third law. The question is, how big is the force that the painter's feet push down on the ladder? Well, in this case, if we look at the painter, the normal force pointed up is the only up force on the painter. The force of gravity on the painter is the only force down on the painter. Since the painter is neither accelerating up or down, that means all forces on the y-axis have to cancel, which means that the normal force acting on the painter is equal to the mass of the painter times g. Since the normal force acting on the painter is equal to mp times g, then we can also assume that if the normal force is pushing the painter up, the painter is pushing down with that same amount of force. Therefore, the force pointing down on the ladder because of the painter is equal to the weight of the painter, which is where I get the mp multiplied by g. Let's next do the free body diagram. All I'm going to do is I'm going to take the different forces that I have drawn, and I'm going to draw them coming from the center of mass of the ladder. So that's going to be approximately here, if we assume it's a uniform density ladder. Now let's start moving these forces to the proper location. And I'm just going to put them at the center of mass. Now, I had no numbers to work with here, but I tried to draw these somewhat to some reasonable scale. If the ladder is not accelerating, either up, down, left, or right, that would mean all forces on the y-axis have to cancel out, so the 2 up forces cancel with the 2 down forces, and then all forces on the x-axis cancel. So the force to the left would need to cancel with the force to the right. That would be a complete free body diagram that would describe the linear motion of the center of mass. Once again, since the center of mass is not accelerating, then these forces must all cancel out. Now, looking at the forces drawn at the point of application, what we want to consider is whether or not the ladder would start to rotate about its center of mass, which is slightly different than actually having the center of mass accelerate. So now I take these forces and I say, okay, where do they go? When we do the gravitational torque, you're always going to put the weight of the possibly rotating object at its center of mass. If the pivot point happens to be off of the center of mass, that means the gravitational force would create a torque. If the rotation point, the pivot point, is at the center of mass, then the weight of the object itself won't actually matter. The normal force from the driveway is applied at the base of the ladder. The normal force from the wall is placed at the top of the ladder. The friction force from the driveway is also at the base of the ladder. Fix this one. The friction force between the wall and the ladder occurs at the very top of the ladder. And the painter's feet pushing down on the ladder occurs up here. And so if you were asked to draw the forces at the point of application, you just need to think about, well, where is that force actually occurring on the object? Because that's going to be important in terms of determining whether or not the object starts to rotate. In this case, since the ladder is not rotating, if we were to go through and calculate all the torques acting on this ladder, we would find that the counterclockwise torques would have to cancel out with the clockwise torques. It would be a little bit tricky here because all of our forces are actually going to be at angles to the r vectors, and so the calculations would be kind of tricky. You most likely wouldn't need to do anything this difficult in terms of calculations, but you do need to be able to think about the forces. There have been AP problems in the past where they've asked people to think about what forces are present and what forces cancel and what would happen with torques. So the drawing here is something you would have to be able to do, though I would doubt that you would actually have to do any calculations based on this particular picture. I think torque calculations would be a little bit easier if those are given to you on the AP test. All right, so that covers pictures that you need to be able to do with forces. Either free body diagrams, which you've done for a long time now, and now just drawing the forces at the point of application. Either one is a question that could be asked on the AP test, especially in a free response question. So make sure you read your questions carefully and draw the picture that they're asking.